started on the second session. Jim's going to talk about lining considerations. Get it up really high. And after classes, work from here.
Oh, right. So
Rather than the other
yeah.
side.
Okay, to kick off the second session, I'm just going to kind of give a bit of an introduction, I suppose, into the tunnel lining, as I've called it, or the jacking pipe design, or the considerations in design. And then following me, we've got a couple of presentations from some of the manufacturers that actually provide the pipes themselves. So they're manufactured in a variety of materials. You can see at the top there, precast concrete, clay, and then GLP. In terms of the jacking pipe itself, and then again, just to clarify, when I'm saying jacking pipe, it's a continuous pipe. So if I refer to a tunnel lining, it is a tunnel lining, but not segmented. So in terms of what they need to cater for, they need to cater for the permanent loads. So when you've installed the pipe and walked away, that includes earth loads, hydrostatic, so that's the water load, normal traffic loads, so if it's in a public highway, HB45 loading or whatever you may have. And I've got down there any special surcharge loading. So railway loading is something that is an extraordinary loading, if you like. Now it's defined, I think there's a standard. There's a GT standard, a network rail, or a group company standard, something like GTC 5217, I think. Now that actually tells you how to calculate the loads. There are other documents, such as in the back of a document called BSEN 1295, the guidance for the design of buried structural pipes. They've got a series of nomographs in the back there, for want of a better term, so that you basically for the depth of cover and then the type of railway you've got, whether it be mainline railway or what they call light railway, you can read up and you can define the surcharge loading. And then importantly, in terms of jacking pipes, you've got these temporary loads. So you've got construction loads. And when I say that, it's predominantly from the surface, so that could be if you're using heavy cranes that are going to be sat in the area. It could be if you're using very large plant. Sometimes you'll be using, let's say, small dumpers just to run up and down, but then you'll be using the big 6-wheel Moxies maybe. And then at the bottom there, the actual installation loads. So if you like, the permanent loads may be concentrating on the loads that are surrounding the pipe and then being pushed on from above. And the installation loads at the bottom, they're kind of the linear loads, so it's the jacking process itself. In terms of the importance of that, just on the side there, this is basically the mechanism. So you've got a pipe in the ground. So the pipe at that stage, if you've not considered your design properly, you may start to get some cracking. They may or may not be visible, those cracks. That's within the line. And this is, I would say, for a rigid pipe system, which most of the jacking pipes are. In stage 2, you can see that you'll start to get a little bit more cracking, and that can lead to infiltration of water. And importantly, if you were to get this mechanism of failure occurring whilst you were doing the pipe jack drive, that would cause you an awful lot of trouble if you've got loose materials, sands and silts and things like that running in. And then ultimately at the bottom there you can see, so it's perhaps your worst nightmare. Certainly during construction, that'd be something that you wouldn't want to get to site to. But if you've installed your pipe jack, you've handed over the keys to the client, and then 12 months later he rings you up and says that we've got a problem, and you get that scenario, then that's just a complete failure of the pipe where hinges have developed, and it's got to be replaced. So just simply, again, for the rigid pipe, these are the key things. You've got load coming down from the top, and you've got some ground resistance. This is schematic, so it's just got ground resistance at the bottom, but the ground resistance generally is all the way around. And then you've got the positions, if you like, the critical positions of your maximum moment. So typically in the invert, the crown, and then as we refer to it, the springing level of the pipe. So these are where the bending moments will potentially be greater. There's an importance in the fabric of the pipe, if you like, or when the pipe's installed, and the serviceability of it is that the jacking pipe goes through, and you'll hear later on, I think probably from Graham or some of the other guys, about the fact that once you've installed it, you will background. So there's the machine cuts an annulus around the outside of the jacking pipe, and it's important that is filled once the operation's finished. The bentonite is placed and that's filled, and that hopefully allows for the ground load, the overburden load, to come on uniformly around the pipe there. It's important that the loading is very important to have a look at and to understand when you're doing the design. So in soft ground, and I'm not going to go into the specifics of these, but in soft ground, and I've called it a traditional loading model, might apply. So it's kind of a typical soil arch. People refer to maybe familiar, with the likes of Bolton, Tazavi, who champion these different methods. This is very, very kind of simple model, I suppose, and then Tazavi developed that to be a bit more representative of what you might get when you're looking at soil arching. If you're into rock and things like that, again, I've included a reference there for anyone that wants to go into for it. But you can look at more complex loading. So again, it's a bit of a variation where you're looking at the tunnel itself, and then you're taking load off the side, and you've got the arching effects. In terms of loading, it's very important to understand the conditions that you've got, because as I'm sure you can appreciate, if you were loading a pipe in the ground, and all you were ever doing was considering, say, a full overburden depth, then you'd be shattering pipes all the way through the country. And in practice, that's not what happens. Maybe in a loose sand and gravel, yes, and if you say at 5, 6, 7 meters deep, you could be picking up most of the load. But certainly, as you get deeper, then if you like, the system needs to appreciate that you do get arching. I often say to people, when you try to explain it with the soil arching, it's if you're doing something on a property at home, you can take so many bricks out of a wall, and the structure will arch over it, and you won't get any cracking. You'll get to a point where you take that many out, you need a lintel. Groundwater is very, very important. Ground load can often be considerable. It's certainly probably one of the dictating factors of load. I've put this photo, and this is a job that I was involved with a few years ago now. And it's a water company job. So the water company, as many of the water companies are, specify that the design groundwater level needs to be, the design groundwater needs to be at ground level for the shaft. But you can see there, this is down in Ramsgate. So you can see that you've basically got a cliff face there, and you've got the bedrock down here, and then you've got the superficials above. So when you looked at it, this is a chalk cliff with smugglers' mines in there. So you can actually see where the old adits have been put, and you can see water runs out there. So really, there's no possible way that the groundwater could ever get to there, because it'd be free draining out of there long before that you had that situation. And that's just one example of how sometimes you could potentially challenge the standard, or how things might not appear as they are. But also, you need to sometimes think if you're in a floodplain. So I'm thinking about up in Yorkshire a few years ago, where for quite some extended periods of time there was flooded water. So that will obviously give you an increased water level, and then there's a trade-off there with buoyancy effects, which you need to have a look at. So generally, you determine the forces in terms of the overburden load and the water load. You determine the forces which are acting at the crown, the springing level, and the invert. And then you check stress utilisation in pipelining at critical points. That's generally what the design comes out with now. In a reinforced concrete pipe, that would be an M envelope. So I think I've got there. So you'd plot the M envelope. So you'd plot axial force against moment, and as long as you're inside that graph, it's kind of happy days. The pipe will work. With other materials, it's the same. It's just an equivalent that you're just looking at the stress. I've just put that note at the bottom. This is, if you like, the kind of the first principle way. But at the bottom there, again, 1295 considers buried pipes. It considers, or it's got a formula in there to calculate the effects of earth load, water, surcharge from construction, and it's got surcharge from railways. But that document was designed predominantly for open cut methods. Now, its sister document, which I think is 9295, off the top of my head, that does have a very, very small section in there about pipes that are installed by treacherous methods. And I mean, I think in short, basically, for those of you that are familiar, in terms of the pipe bed, it comes in classes, and a fully encased or a fully surrounded, well-supported bed is a class S. And so really what happens is that standard kind of tips its head towards that, but I would certainly recommend that for more challenging jobs, perhaps if you're deeper or perhaps if you're in very poor ground, you probably should be trying to look at it in a little bit more detail. The jacking pipes are subject to large axial forces, or can be, during the jacking process. That's just a shot of them. That's the main jacks in the pit. And the manufacturers will typically give you maximum design loads that you can push through the pipes, with an appropriate factor of safety. And then they'll also tend to give you a steer on what those loads are if you get any misalignment along the pipeline. Again, I'm not going to cover anything about it now. I think Graham's going to talk about it later, but you can use interjack stations to manage loads along the pipe string. So this is it's not the biggest graph, but that would be the predicted jacking load going up, and you can introduce intermediate jacking stations which allow for the load to be dropped, and that it helps to combat against friction, but also it helps to safeguard the fact that the load's not going to rise up when you're going to start smashing the jacking pipe. So you need to check the pipe. We've talked about that you've got to check the pipe in its permanent case. You've got to be happy that it'll take all the loads. But in the case of jacking, as I say, if you push in directly, so if you're jacking the pipe into the ground, there's a straight axial force, but you need to allow for some misalignment. Joints can always be at a slight angle, typically 0.25, 0.5 and up to 1 degree are generally what the loads are that are provided for the capacity. But in terms of the pipe, you can see that schematic that if this is one pipe and that's the next pipe, and you've got outer tolerance load on there, you may be getting more load or more stress on that side of the pipe. So it's a check that's worth doing. So it's important to consider and select the preferred material. They've all got their own benefits. I won't touch on those. We'll hear from that shortly, but they've all got their own benefits and they've all got their own limitations. So you should be thinking about why you want that. Dare I say, cost is a big driver, but it shouldn't necessarily be the dictating factor. You need to assess the load in both the temporary and permanent cases, and then compare those assessed loads against the capacity that your product pipe, whichever material it may be. And then be mindful, consider the installation tolerances. And again, as I mentioned earlier, and it's a theme that I'll keep coming back to at any stage, whatever you're doing. If you're doing a calculation, calculations are very often based on some assumption. So if you're not sure, this is the time to not necessarily just say, oh, well, I'll assume that. You maybe pick the phone up to a pipe jacking contractor, or indeed hopefully you might have your contractor appointed, but you go and say to them, what do you think about this? What tolerance do you think you can hit? Do you think you'll get any misalignment? Hopefully they're an honest enough crowd to say, well, this is typically what we get, or they might be able to give you some data to prove the tolerances that they've achieved in the past. So whichever it be down there, excessive load is risk. So if you get excessive load during your jacking process, ultimately that can lead to a stop. So you need to really advise the contractor on estimated jacking loads when you're looking at the temporary case. particularly where you're going to depend on interjack stations. Now I'm going to be talking a little bit later about the backwall design and then how those loads are derived or how they're looked at in the temporary case with regard to kind of face load and friction and things like that. It's important to note that just to close off, there are other factors as well that will affect the ability to put load through the pipe. So you can load a jacking pipe up, but remember we're working on a hydraulic system. Those hydraulic systems have certain limitations on the bar that you can run through them. So you can't ultimately just keep knocking the pressure up and up and up and just trying to hope it'll push through. And again, it's a bigger thing. But if your jacking forces are going up, then potentially you've got other issues to do with the way that the machine's mining and things like that. But again, all of that comes back to the pipes. So you want the pipes to go through, you want them to be structurally sound, no faults in there, no defects, and then that'll get you from A to B. And I'll hand over to...
Thanks a lot. Yeah, we won't take any questions at the moment. We've got 2 more sessions on pipes and design of pipes and joints. So we deal with Duco.
Okay.
Can you get it up as high as you can? That's it. Can you get it on there?
Good.
That's forward, and that's the pointer.
Okay. Good morning all. My name is Duco. I'm from the Netherlands. My English, I'm not a native speaker, so excuse me for that. I want to tell you something about the jacking pipes, the GRP jacking pipes, glass reinforced fiber jacking pipe. Oh, wrong one. First, the general, what are GRP jacking pipes, the product and joint design, some features and tests, standards, guidelines, of course, and installation. You see an example of a GRP jacking pipe, DN3000. Our product ranges from 250 till 3600. The design. GLP is a thermosetting plastic, and we use resins, in our case polyester resin, glass fibers, and additives like sand, etc. And we have a recipe, of course. You produce in layers. Here an example. You've got an external surface, an outer reinforced layer, a core layer, inner reinforced layer, and a liner. Actually, with this structure we make in HB. That's the principle. So we have a lot of glass reinforcement in the outer and the inner reinforced layer, and in the core there's less glass. And the liner is for protection. Production process, centrifugal casting. So we get a fixed outer diameter, and our inner diameter can be adjusted. When we have, for example, we start with a ring stiffness of 32,000. For a DN1000, then you have to think about the wall thickness about 40 mil. But we can go to a ring stiffness of 100,000 or more. Then you get a wall thickness about 60 millimeters. With that, plastic pipe, flexible. No. When you talk about a ring stiffness of 32,000, it is a semi-rigid pipe, and above 64,000, it's a rigid pipe. So GLP jerry pipes are rigid. A nice example from starting kit. Joint design. We have for gravity pipes we have two types: a GLP sleeve and a stainless steel coupler. But we can also make pressure pipelines for jigging: PN6, PN10, PN16. That are the operating pressures. For testing pressures, then we are talking about PN6 and 9 bars, or PN10 is then 15 bars. And of course the interjack stations, but they are custom made, what the jacking contractor wants. An example of the GLP sleeve. Picture. So we have a groove in our spigot, and there's a rubber seal in. Just like with the concrete pipes. The stainless steel coupler is a fully embedded rubber seal in it. For the pressure, then it's different. We have two lips for the pressure applications. An example of an intermediate jacking station. There's all the jacks in the building. Our product range related to the coupler. The GLP sleeve goes from 400 up to 3600 for gravity. The stainless steel from 200 to 250, actually to 2000 to 250. And the pressure applications are from 300 up to 2500 and 2000 and 1600. Why is that? PN6 pipe from 3600 is, well, that's too much. Joint performance. When we have a gravity pipe, PN1, we have testing on our joints 2 times PN. So a PN1 gravity pipe is tested, the joint is tested at 2 bars. This is an example of a PN16 pipe, so it's tested on 32 bars. There's a big difference with other pipe materials. I know for concrete pipes, for example, they test on half bar in joint, with gravity. We test in 2 bars. Jigging loads. We did that in the past, a lot of testing on the pipe ends. How react in GLP jigging pipe when it's actually loaded, and not once but 1,000 times. Then you see, and with also with angular deflection between the joints. So, yeah.
So what is that graph showing on the right?
This is stresses, the compressive stresses. Red is high.
Yes, it's the eccentric line. Yeah.
This is something got hideously wrong.
Yeah. Other tests we are doing is, of course, initial long-term test, but also the long-term strain corrosion test. And you see in this picture an example. And we do with sulfuric acid, we are testing with a pH of around 0. And it's a long-term test, that more than 10,000 hours. After that, we go to burst for, to see what the strain is left on that moment. Hoop tensile stress test for pressure pipes. We go to burst pressure. For example, PM10 pipe has a burst pressure for approximately 45 bars. Standard guidelines and quality specifications. There is an ISO standard for jacking pipes from GLP. We have several quality specifications, like from TÜV or from Belgium, Beno. There's a product certificate, and our pipes are every week tested by external parties. And the last one about static calculations. The 161 from Germany is the most advanced guideline on this moment for calculating jacking pipes. For the jacking loads, but also the permanent loads, the live loads, like railway loads and aircraft loads. The jacking methods, of course, older microtunneling, but not HDD. Direct pipe, I'm looking at it on this moment. We can now get a question for direct pipe. I think maybe in a few years, yes, but not on this moment. The jacking loads. The GLP pipe, we don't use a wooden packer. We don't want a wooden packer. The difference between the behavior of a jacking pipe with a wooden packer or a GLP pipe without. Straight jacking, which never happens. We have always steering corrections, especially in the Netherlands. We've got with our soft soil. We get the first correction as the machine leaves the startup pit, and it goes down. And with curved jackings, we closed joint situation with GLP. Normally, even with curved jackings, we still have a closed joint situation. So you can max out your jacking loads. Open joint happens too, but when we look at the German guideline, what is saying now on this moment about jacking loads? If we have a closed situation, so in this situation, just closed. If you use a wooden packer, then you have to divide your jacking loads by 3. Without, divided by 2. So what you can push on the pipe is then a big difference. We're talking about benefits. Because of the production process and the polyester resin, we have very low wall friction. Design value is normally around 5 kilonewton per square meter. In practice, you get 2.5, not high. So your jacking load on is less. higher jacking loads allowed. Also with the closed joint situation, we have more closed joint than other materials. In the larger diameters we can do longer jacking drives, up to 300 meters. If that's smart to not using in the jack station, that's something else. But in theory we can make a jacking of 300 meters. Our outside diameters are much more. As I said, we are thinking about a wall thickness of 60, 80 millimeters, no more. Durability, very corrosion resistant. Lifetime, 100 years plus. Life loads, for example. In the Netherlands we do about 40 jackings a year with railway crossings. We have there a market share of between 80 and 60% with jacking. In the total market we have a market share of about 40%. Schiphol Airport, and there's a crossing, GLP. Thank you. Any questions?
Duco, you showed us the centrifugal method of manufacture,
Yeah.
and I noticed the two product certifications, the two from the bin are both for Hobas pipe,
Yeah.
which is the centrifugal method.
Yeah.
Can you also make jacking pipe with the flow type method, which is cast on a mandrel?
Yes, but to be honest, the Hobas pipe is more advanced. We have more, the wall friction of the flow type is higher. It's not, they can do it, but it's not our favorite. Also, we can do it, but we prefer Hobas.
Okay, thanks.
We have also much more experience with Hobas than with flow type. The Hobas worldwide we do a lot. Also in Belgium, France.
Right, thanks.
Okay, thanks a lot, Duco.
No.
Can you stand on that side?
Oh.
That side. Just forward, and that's your point.
Sorry, which is forwards. Yeah, that's what okay. Morning, my name's Mark Crawford Jones. I'm from Stanton Bonner, manufacturer of precast concrete jacking pipes. Just a bit about Stanton Bonner. We're part of the Consolis Group. They're a £1.4 billion pan-European precaster, so cast everything from pipes to bridges to building facades and that sort of thing. We're based in Ilkeston in Derby, and we've been there for 100 years, just celebrating our 100-year anniversary this year. So we've got a bit of a history for pipe making. I've been with them for just under 20 years, so still a newcomer to them. And I've been dealing with the jacking pipe since most of this time anyway. Been an established member of the PGA, and we manufacture a range, well, in the market you can get a range from 450mm through to 2.5, and Stanton Bonner we manufacture from 1200 through to 2.5. We're currently the framework supplier for Thames Water for all their jacking pipes, 1200mm and above. We've had that contract for about 20 years, so pretty established. Over the years we've provided lots of major schemes, the Olympics, the VRP project recently, so we're pretty knowledgeable in what we do. Just want to talk a bit about the manufacturing process. In the market, there's two ways of manufacturing the pipe: a wet cast or a machine cast. Stanton Bonner machine cast all our pipes. So simple ways, it's just like making big sandcastles. So the first slide shows that we've actually got a pit in the floor, and that's the actual outer mould and one of the fittings. We then get a press head that comes down that forms the other socket, and we apply a vibration to it. The whole pipe then comes out of the ground with the mould, and then it's demoulded, and then that mould goes back and is used again. Now, one of the reasons we went down the machine cast route is wet casting, the optimisation of moulds, you have to wait for it to cure before you can strip, before you can move on to the next one. Whereas this, we can get a bigger output from pipes from a limited amount of equipment. Helps with production planning, because if you've got a short window to manufacture, you can go in and manufacture a volume and then move on to a different product, rather than having to tie up the production for a long period of time making one sort of pipe. All the pipes are manufactured BS5911 and can't mould them accordingly. It's a spigot and socket profile joint with this mild steel collar, which you then fit an EPDM gasket onto the spigot profile, and then this is rolled into position during the installation. Mild steel collars fitted as standard, but we can also fit stainless steels or other materials if needed. Now the collar is always seen as a magic, a specific thing for the jacking pipe, but in reality it's just there to provide a compression on the gasket and also to prevent anything from externally coming into the joint. Come in two variations: a plain pipe and an insert pipe. Most people call an insert pipe a grout pipe. So throughout the pipeline, you install a grout pipe or an insert pipe, and that enables you to either put a lubricant while you're installing the pipe, or subsequently grout to fill the annulus once the pipe's installed. Standardly coming at 12 and 2 o'clock, but we can make different variations if need be. You don't get to see them very often, but this is actually a grout socket that we're casting. If you want to have a look and a look around, it's not the most exciting thing, but it's something that you don't really get to see very often. We've touched on interjack stations a little bit. So the interjack station works as a whole, but comes in two parts. So you've got the lead and you've got the tailpipe. So once your jacking forces in the main pit have been approaching where they want to be, you can then install an interjack to have some intermediary jacks in there to spread the load along the pipeline. So, as you can see here, so you get so far through the drive and you install the interjack and you put the jacks inside the interjack station. Those extend to push the pipeline along, and then they're closed up from your main drive. You then strip out the jacks and close the interjack station up so it works as a whole, and then you wouldn't really know it's there in the pipeline. We've talked about curved pipelines. The joint in the pipe allows a 1 degree deflection. So you can go around the curves, but careful consideration should be taken on the jacking forces when you go around a curve. The joint deflection really affects how much of the allowable jacking forces onto the pipe. So, as I've got a bit of an example at the bottom, if you're doing a 100% straight drive, you've got 580 ton maximum allowable force on a 1200 jacking pipe. With a 0.9 degree deflection, that drops down to 300 ton. So, you may think you're going straight, but if you do go offline and get a deflection, then that'll have a big effect on the forces that the pipe will take. So this gives a bit of an example. So as you can see there, the stress is there as you start to deflect. So you really have to be careful to make sure that that load is taken into account when you're doing the drive. Being part of the Consolis group, which I mentioned earlier, gives us access to a pipe called the Bonner pressure pipe, which is a pipe that's really designed for pressure applications, power stations, sea outfalls, that sort of thing. But you can actually jack this pipe, and it comes in up to a diameter of 4 metres. I won't touch too much about it because it's not that common pipe, but the pipe is a solid steel core with a concrete lining and external coating. So the steel core is the pressure part, and then the concrete is there for the sleeve. So it comes in two joints, your classic gasket joint or a welded joint. Sometimes where you've got either aggressive ground or what's been going through the pipeline, you might want a welded joint, offer a little bit more protection for the pipe. So that's the two joints. So the left-hand one is a typical gasket, and the right-hand side is a plated welded joint. Now, something that we're quite interested in is instrumenting pipes to gain information for maintenance, production and traceability. So by putting RFID chips in pipes, you can actually trace it from production to installation. You can also have chips in pipes for maintenance, so you can actually scan the pipe with a handheld device and gain the information from that. So really moving away from a paper-based maintenance and record keeping to an electronic based. So we're really keen for people to come to us with ideas of how we can instrument pipes or put sensors or other equipment inside the pipe at the production stage that may be of benefit once the pipelines have been installed. Any questions?
The sensors you're saying about putting in the production phase,
Yeah.
have you had any success in that? Just curious about the vibration in the dry cast process.
Well,
Potentially damaging things.
the experience we've got at the moment is with the Paris Metro.
Yeah.
So part of the brief of the Paris Metro was being able to trace the product from production to installation. So there's a simple RFID chip that goes in on the manufacturing once we're producing the pipe, and that gives the segment a unique reference. That unique reference then can be used to locate it in the yard for loading sequences, and also when it's actually installed, if there was a problem with it, then you can scan it with the RFID and then take that information all the way back through the production to find out which batch, when it was cast, is there a wider problem with that product.
You mentioned about the linings on the inside of the concrete pipe. What sort of linings do you do?
The lining is a concrete lining, but we can actually put a plastic lining in there as well. So if you've got an issue, as an example for H2S, then we could put a plastic lining inside to protect the concrete. The inner surface of the concrete on the pressure pipe is really sacrificial. So the external outer core has got this reinforcement in it, and you've got the steel, solid steel pressure centre, and then the actual internal lining is really a sacrificial lining.
Any more questions? Okay, thanks very much, Mark. Back to Jim. Can you stand this?
Okay, we are getting towards some of the construction related and the process related talks, but I'm just going to do a little session on the shaft design, because at the moment we've talked all about the pipe jacks itself, if you like, the line and the tunnel, or the tunnel line. So pipe jack tunnels and micro tunnels can be driven from a variety of shaft construction types. So you've got segments, precast concrete segments. That comes in either a jack case on or an underpin. You can see there. That's the lining. Again, the lining. This is creating an under-ring base, whereas that's just a case on to depth with a mass concrete plug in the middle. Sheet pile cofferdams, as I'm sure many of you have seen. CFA or C-compiled shafts, I think someone mentioned earlier the Newark project, and this was a secant pile shaft on Newark with it's got a concrete tip fill at the bottom. That is, yeah, that's the jacking shaft one to the pumping station. And then on the grander scheme of things, we've got diaphragm walls. I mean, I've got another slide on that. They're probably the bigger end of things, but again, perfectly good shaft from which you can drive out of. And then obviously, in the right circumstance, there's a battered excavation. If you're doing, say, a shallow kind of drift almost, if you're doing a bit of treacherous work, where maybe ground movement isn't as critical. So it could be, for example, going under a site of a triple SI site, a site of special interest. Obviously, settlement and heave are big considerations, but if you were to get a little bit of settlement going under, say, a green field where you were just trying to minimise disruption to the public, to the flora and fauna, that wouldn't be as critical as if you were going under, say, a railway where you were predicting, large amounts of settlement and then risk to the rolling stock. So I've picked on a few points out of the different methods. So when you're looking at your shafts, the thought should always be what the depth of formation is, and then the adequacy of that system for earth and static earth. So, for example, I'm supposed to take an extreme. Clearly, if you were trying to put in a shaft to 35, 40 metres, it'd be somewhat of a challenge to put a sheet pile coffer down it. You'd probably find that by the time you were, past 15, 20 metres, you were going to be starting to struggle with frames that's so close centres it'd almost be like fully closing a heading. The ground conditions, again, that's the theme, I think, of a large part of what we've been talking about. Ground conditions dictate risk. Risk dictates many things, including the success of the scheme. The need to control groundwater. So when you put your shaft in, there are different phases when you actually constructing the shaft. Groundwater can cause you potential issues. When you get to the base, it can cause you issues, and then when you're trying to get in and out of the shaft itself, it can again cause issues. In all of this, I mentioned, and we've just had the presentations that just talked about the temporary jacking load. So when you've got the rig in the bottom of the pit or the shaft, and you're going to push forward, you put in a load which will effectively go onto the back wall. Again, I'm going to touch on that later. Okay, there is normally, or hopefully, there's ground behind the shaft that's taking out, but the lining still does have to do some work. I touched on it briefly. So the method of exit and entry and the sequencing and the methodology needs to be thought about. So I gave that example about groundwater when you were breaking in and out of the shaft. So if you've got exceptionally high groundwater levels, or perhaps artesian pressure, you may choose to sink a caisson shaft, and you may choose to put what they call a carcass or a jacket on the outside, an unreinforced amount of concrete, so that when the shaft's in the ground you can safely break out the rings and still have some protection from groundwater. That would be a specific method and sequence that you may choose to consider. The need to provide a shaft iron. So if you've got a shaft 6 metres, 7 metres, whatever it might be, and you're going to knock a hole out of that shaft, you need to think about that. So if we've got say an 8.2 metre shaft and you were going to drill a 150 hole in it, granted you should be quite happily drilling away and have no problems. But if you are trying to receive a machine and you've got to knock a 2.5 hole out of that ring, that's a different thing in its own right. The way that the earth load will come on and it will act as a hoop, so you will get force travelling around the ring. So if you take too much of the ring out, then you might not have enough capacity in the segments to actually carry the load around that open, which will lead to cracking and ultimately failure. So you need to think about how you support that eye, if indeed you need to. And the working space that's needed in the pit bottom. So the manufacturers provide shafts in typical diameters or a standard range of diameters. I'm sure you can get specials if you were prepared to pay for it. But the working space will often dictate the arrangement. And again, it's not just the working space, so I'm talking about shafts, but again, pits, so it's the shape, whether you need it to be rectangular, square, or indeed circular. So segmental shafts, it's just some aspects to consider. When you sink the shaft, if it's as a caisson, or indeed if it's underpinned, but you create a gap behind the extras of the lining and the ground that needs to be fully backgrouted, particularly where you're going to load it, because if you've got a shaft and you've got the ring coming round and right where your jack or jacking wall's going to sit, you've got voiding behind there. As soon as you push it, then the joints of your segments will want to kind of rotate, and it could lead to a failure. And I've already mentioned there, so where sections of the line are going to be removed, you will get a stress redistribution, and you may need to think about how that's managed where you discontinue the unit. So in essence, as I said, if you've got a metre deep unit, and you take a hole out of it, as the load comes round, it will want to flow around that opening. And if you haven't got enough of the ring left to carry the load in terms of the area of the concrete, then typically you need to do something to reinforce that. And it could be channels, parallel flange channels that are dialed in so that the force is captured and transferred through the dowels into those sections. Or very often it's driven down a pattern of kind of studs, and then it's a reinforced concrete head wall, so as the load goes around, it's transferred past the opening. Managing water during the formation of the entry and exit eyes, as I touched on there, that's critical. The machine has to get out. Again, Graham will probably pick up on it later on, but the machines won't particularly like going through reinforced concrete sections. You might get away with fibre, if it's a fibre ring, but if you've got reinforcement in the shaft lining itself, that will need to be broken back before the machine's launched. And so in doing so, you're creating a path between yourself and the ground, so water's critical again. Need to think about dewatering during shaft construction, where dry conditions are required for underpinning. So if you're going to underpin the shaft, it's got to be free of water. If you jack the shaft down as a caisson, it can be in the right kind of conditions. It can be sun wet. So if you've got water coming in, you dig through the water till you get to the bottom. You can pour a mass concrete plug underwater and trem it, as they say. And then once you pump the water out, that's cured. You pump the water out, and then you can fit or construct a reinforced concrete base on top of that. When caisson sinking, it's just important to understand the potential for the shaft kind of hanging up or getting stuck on cobbles and boulders. So again, if as I just mentioned, a wet caisson particularly, if you're intending to dig through water, you haven't got access necessarily to clean out where you're going, and that can be a big problem. So on the left there, that's a glacial deposit. So looks like a decent enough clay, you'd be quite happy going shaft sinking in that. But that's also a glacier deposit as well. So that links back into what Dave was saying earlier about when you've got SI, it is important that you get someone to have a look that kind of does understand what they're being told, because if you just look at a borehole or you look at a map and it says the glacier deposit, and you've got that in your mind, then that would be a much more challenging kind of terrain to drop a shaft in. And certainly, if you get some of these boulders under the cutting edge, you'd be struggling. So just briefly on the sheet powered cofferdam, you need to consider drivability of the sheets for the ground that you're in. Again, if you think about that slide I've just had up there, trying to drive sheets through cobbles like that, it's probably not going to be a clever thing to do. You need to think about the wailings, the struts, the intermediate support that goes in there. This is it's a cofferdam or a secant, so on a secant part you may need some intermediate beams depending on how the wall's designed, whether it can be designed as like a freestanding wall or not. But the point is that you don't want any of these things to impede the jacking process. So again, if there's no point in you having a series of supports in right at tunnel access level where you've got to be putting the jacking. The pit wants to include for corner piles, and sheet wants to be interlocked. That mitigates water ingress, it stops that, but again, remember, particularly on the drive shaft, the stability of the shaft or the pit is everything to your jacking process. So once you bring that load on and you start to push, if that wall moves at the back, you're going to be in a lot of trouble. So that it's very, very important with a cofferdam that it's not just, if you like, a few trench sheets dug in with a couple of supports. It needs to be a more formal structure. And it's always important to think about base stability in the design. Again, I'm sure many of you have perhaps used the piling handbook. That gives indicative lengths. It actually gives a formula, I think, for working out the kind of toe-in depth that you need. It is a bit of a rule of thumb because you can do proper seepage analysis and things like that to advise on the water cut-off that you need. The importance of that is obviously if you've got a high groundwater level up there and you've got a flow net, if folks can think back to the days at college, you've got the flow net, so you've got a water pressure up there, and if you've not got sufficient cut-off down there to manage that water, then you, in the wrong ground conditions, so in granular materials, certainly sand gravel, you could get boiling. I mentioned D-walls. I've just said there, maybe fair, maybe not, but whilst it's one of the more expensive techniques and it's not routinely used on smaller projects, as I say, I think that's fair, it gives you a really robust lining. These things are typically probably 0.8 to 1.4 is maybe fair to say is kind of a typical range. This is a shaft being dug, and you can see this is the grab. So this was 1.2, so the grab stands at about 8 metres tall, something like that. So very large equipment that's needed. It's for those that don't know, diaphragm walling is a method where you dig a trench. That particular job, I think they were 42, 45 metres, something like that. So the grab digs panels. So if you like, the shaft is a 50p piece kind of shape, if you know what I mean. So you dig it to the depth, and you keep filling it up with bentonite. The trench, the panel is fully supported with bentonite till you get to the bottom. And then when you get to the bottom, they put in some stop ends so that you can go on to the next bite, as they call it. But basically, they then send concrete down tremie pipes and fill it up from the bottom. And take the bentonite away. It's reinforced during that time, a bit like you would do with a reinforced secant pile. On that one there, as you know, it's worth you knowing about it. The size of the plant and then all the supporting backup can probably be a bit onerous. So you're maybe going to struggle on a smaller site. But as I say, these things do tend to be the more expensive. One of the benefits with these, as with other things, is you can actually, I mentioned about breaking in and out of the tunnel. Also in and out of the shaft to construct the tunnel, and the issue about controlling water. So what you can do in a D-wall shaft, because you put in the thick permanent lining in the first hit, but you can construct what they call a soft eye. So if you think about as they dig in each one of these, you think about a 40-metre deep panel of concrete going in, and then you put your reinforcement down. What they do is the soft eye is typically made out of a GRP material. And that means that the tunnel machine can mine through it. So in summary, the prevailing ground conditions and the depth of the shaft are often the things that will dictate which construction method that you should use. And in a different vein to what Dickie said earlier on, you shouldn't be choosing your shaft construction method purely on cost. It should be to suit the ground conditions. Each one's got its own advantages and disadvantages, and they'll be specific to each and every kind of site it works. No, it's not fair to say that on 10 jobs that one method would be suitable for all of those. And you need to consider them at the earliest possible stage of the design. In the temporary case, water management may be required. So again, I come back to what Dave was talking about. So understanding water is critical, and if you don't undertake a proper assessment of it, you'll most likely have issues on site. So they're critical to success. Importantly, they allow the pipe jack to be safely launched and received, and then from a client perspective, or the end user, they're very, very often part of the permanent work. Some shafts or some pits are put in and they're temporary, and they're either filled in or they're taken out. But I'm sure a good percentage remain as part of the permanent work. So it's what the client's left with, and that will be linked to a design life or an operating life, and that's got to be serviceable for the client. Now, Dave's going to talk a bit about ground movement.
Has anyone got any questions? Because we haven't got a bit of time if you want to ask a question now.
Yeah. Good morning again, just checking. Yeah, let's talk about ground movements. This is another thing that as geotechnical engineers we get asked to look at, as well as the initial review of the GI, developing a ground model, as what the actual effects of the pipe jack or any other method is going to have on the surface. There we go. Yeah, as the tunnel is excavated, obviously the diameter is larger, the lining is going to follow, so you will have a void generated, called the annulus. The soil, regardless of what it is, will generally close around that lining. How long that takes is dependent on what kind of ground conditions you have. That subsequent sort of movement, that volume of closure, is reflected on the surface. That varies again with ground conditions and how close you are to the surface. The deeper you are, I see Jim touched on that earlier, you have an arching scenario where effectively you're only really going to affect a certain distance above the tunnel crown itself. Again, these are exaggerated, these are so you can actually see them. We're talking sort of millimetres, so not as excessive as those shown there. I won't go into too much detail as to the actual mathematics, that's how we review this. Often we're asked to comply with a settlement requirement or a maximum settlement or SMAX by the authority the infrastructure is passing beneath, be it the Highways Agency, Highways England, Network Rail. Often that's something around about 20 millimetres. And this is a presentation of the results of the assessment of the maximum settlement we'll get. I mean, you can see that's 9 millimetres, so generally that's okay. But another thing that other people may not consider is actual gradient of that curve. If you've got a very sharp dip, you're going to feel that if you drive over a road and there's a sudden 10 mil drop, you might feel a little bump. If that gradient is quite gentle, you may not notice it, and there's a lot of consideration needs to be given to that as well. The width of the curve of the trough, the seven trough I should say, is often a very important factor to consider as well. And again, a bit more maths here, how we work out that. I won't dwell on that too much. The eye basically is the inflection point where you get a convex to a concave, or concave to convex curve. You'll see in a granular situation, which is the top one, the eye value is shorter, so this results in a very sharp and sort of a trough, and with a greater eye value for cohesive material, you get a very wide trough. This is, again, looking into the mathematics of it, don't want to dwell on it too much, but You can see here that sand and gravels produce a deeper and narrower trough than the cohesive. So a lot of the assessments are based on the next couple of slides, I'll see is the new and O'Reilly method, which basically considers whether the soil's granular or cohesive. The parameters of the soil aren't really considered. It's just a very empirical method. It's based on experience on driving in London clay particularly. But it's being sort of adopted by the industry and it's used widely.
Widely or wildly?
Both. So you can see here, if you're just considering the soil type, you've got a clay there, it's a soft clay, you can squeeze that between your fingers, 25 kPa, of a reasonable sand. You've got a very stiff clay, which you'd struggle to stick your fingernail in, you get the same settlement values, same troughs, which isn't really representative. It's very, very conservative. Again, when you've got a layered system, if you've got granular over cohesive, the granular, the cohesive, the granular material is going to have more of a reaction than the cohesive material. Again, this is looking at what Jim touched on, glacial deposits. That's quite a wide description. It could be anything from cobbles, boulders to silts and clays. So adopting values have to be very careful. Again, these are all very conservative. If you look at the methodology, trough parameter can be related to tunnel depth and type using the empirical factors. Again, these K values, all these values pop up and have to be sort of estimated. Even then you've got a bit of a range. So this emits completely a wide range of soil types and conditions. Again, same photographs. Glacial deposit, very hard clay. You can see there's actually marks in there for the excavator. So I'd say that's a good stiff clay. And then you've got, that material. And you can imagine driving a hole through that. It's probably not going to react anytime soon. There will be some settlements involved. It'll be a long-term situation. I mean, that material, it's like drive through a cold chocolate. Whereas that is more of an oxo cube. As soon as you drive through that, it's just going to fall to bits. So here we are. This is how the volume loss is expressed as a percentage of the whole area. This is where we come down to where we can use a bit of our experience and modify the calculation as best to present the actual real world conditions. And it's all down to the volume loss and the lost area values. And if you see here, we have, you've got your silts and clays, if it's soft, firm, stiff, very little volume loss there. If you've got loose sands and gravels, probably worst case condition. It's like an egg timer or an hourglass. If you turn it over, the sand disappears down the hole. Whereas if that was filled with clay, it wouldn't go anywhere. So this is where we can have a bit more input into the actual calculation and have a bit more confidence in what the values were presenting. So we can, in this situation, we've improved the curve by applying some experience and a bit more understanding of the ground conditions to improve the, not necessarily, we can't apply any parameters to the soils as such, but we can estimate the face loss based on the ground conditions I presented and present a better picture. But again, all these are very conservative. I mean, the values that were given to fall within 20 mil, 10 mil, as long as we're using these conservative methods, we fall within those, everyone's happy. And in some cases, you can be just outside those, so there's an option then to maybe take the drive a bit deeper, to give you a bit more sort of overbearing material, which will actually reduce the settlement or indeed widen the trough. If there's any more analysis required, there is always the option of going into more detailed assessment and finite element analysis and 3D modelling, which will give you a very defined result, but that's a bit more expensive and takes a bit longer to develop models and what have you. So as long as you satisfy the criteria based on conservative assumptions, then you're happy. Again, this is the inflection we talk about where the settlements may start to occur. Oops, press the wrong button, sorry. So the trough width advance ahead of the tunnel drive as material kind of falls into the void behind it, so to speak. So basically, again, these are all empirical. This is based on experience and modelling that's been simplified so it's easily to replicate. Settling against about half trough width ahead of the face, depending on the trough width and your ground conditions. But then the steepest gradients is generally the pit we've obviously we're worried about, making sure we don't go too steep a gradients, and that's where damage to the surface occurs. Imagine any kind of structure or surfacing. If it's a nice gentle gradient, it's going to go with it a little bit. But it's quite a sharp sort of curve. It will do some sort of immediate damage apparent. When you can model, if your drive is going through a varied topography, you've got to split it into slices. So you can see here, you've got a slice there, and as obviously this way the cover is reduced, you're going to get a slight increase in settlement there, and as it gets deeper, it reduces again. So it's all more often the case, and this is obviously a very long drive where you haven't changes in topography. Often the case with the back jacket is limited length, and topography roughly is the same across, so it's not necessary to go to too much detail and consider too many options. Again, you can consider the ground surface that changes. If you're coming in obliquely to any sort of surface features, you get sort of asymmetric trough profiles that can occur. But again, it's the number of that, the maximum depth is the maximum settlement, is often the governing figure that the authority wants you to comply with. Again, there's a lot of maths speak in there. Not going into too much detail, but it's all being developed by experience and, again, more detailed modelling that's been verifying these, so these can be quickly applied to give a conservative answer again, that hopefully will fall within the limits. I've seen read all that. So. Yeah, ideally the area of the trough should equal the lost area of the tunnel cross section. In experiments that shows there can be within less than 1%. So although they are empirical, there is some evidence to back that up, and that's why they're still used. And then we can go through to more modelling imagery. Again, showing a varied ground profile where it's you've got two drives as well. Again, the larger diameter is going to govern the maximum settlement, and this happens to have probably the worst case where you've got the larger diameter drive with the shallowest cover, and this is a bit more cover on the smaller drive. But that's, they won't much consider giving that one. That's the big hit, so that'll be the main sticking point, and then we'll have to try and get that to work. Again, with settlements, there's the possibility of heave. If you're applying thrust at the tunnel face for the forward motion, if your forward progress is limited to the force induced, you will, the ground's got to go somewhere. If it's not coming out the back of the machine, it's got to move. You can have situations where heave can occur, again, there's a various considerations based on ground conditions again, and stiffness of the material you're driving through. Again, a lot of maths. This is all basically, we've gone through, you consider the Q, which is the force, there's various, how that's distributed through the ground, and it gives you all different deflections. It does sound, look complicated. It has been verified by modelling, but it's something that we can be applied quite quickly to various ground conditions and scenarios, sort of to limit the heave and keep the force within a limit to prevent that happening. We present that by the minus figures, upward heave. This is the level of the drive, and you can see that it progresses. Obviously the red's bad. It progresses, you can see the actual heave is ahead. This is the tunnel face sort of distance. You can see ahead of the face, sort of 3 meters. That's where it can affect. That's where you get the elliptical kind of model. Should we go back? Yeah, you can see that's where the face position is. So you're kind of pushing forward the material as well. So as well as the ground profile, ground modelling for the contractor and the shaft construction, this is the other elements we're asked to look at. The heave assessment will kind of give you a limit as to the face pressure. So we can, as long as we've got a face pressure is less than the reactive heave amounts are telling you, then it's okay. The final slide again is this further example of where heave can occur. So if you go back to here, see then you've got a situation, you've got a bit of settlement occurring behind the tunnel drive as well, so as it sort of often will heave, and then as you've gone past that section, the heave will drop. So it's almost like a wave passing through along the line of the drive itself. But again, it's all these things have to be considered, there's limits have to be defined, especially in situations where you have services and structures. I've given you examples of the limits given by Irish England and Everrail, which are fairly easy to contend with because you tend to be passing those things at a right angle. So you've gone past, you've gone underneath the maximum settlements for a brief moment, effectively. Where you've got built-up areas and a lot of congested infrastructure, both underground and overground, then there's probably a bit more detail required. That's where your 3D modelling and your finite element would come into it. And obviously you need to know a bit more ground information as to where foundations are, where there's other services. There could be other sort of tunnels within the ground profile that have to be considered. So that's just a little touch on what we have to consider and how we go about it. I haven't dwelled too much on the maths for you because it's not probably the best time of the day to be looking at that kind of thing. But yeah, you can see it can get complicated sometimes. Some instances it's quite straightforward, but when the ground profile changes and the ground conditions aren't favourable, then there's varying degrees of investigation has to be taking place. But yeah. Okay, any questions? Okay.
I've got a few
No, go on.
follow on. So you mentioned O'Reilly and you and finite element analysis. What's the relative cost of a finite element analysis?
It's
Just say for a simple rail crossing, if you were to do.
well, so if you look at an RLNU assessment,
Note this down.
if you've got the I spoke to Jim the other night. If you've got the ground model,
Yeah.
it's almost like a very hand calculation to some degree. You've got the model developed. It can be a half-day calculation, whereas a finite element, it can take a day or so to develop the ground model, apply all the elements. So you're looking at sort of, easy 3-4 times the cost,
Okay.
maybe more, because the more complication you get, there's more checking and the rest of the process involved.
I would add to that. A lot of people get very excited about FE and want to do it for everything. Yet if you've only got 2 boreholes, if the extent of your site investigation is 2 boreholes, you might not necessarily have information or yield a better result with the FE analysis. It's a bit like rubbish in, rubbish out. That's what people think because they're getting fancy computer output. It's all good stuff.
Answers to 8 decimal places must be right. Is that what you're saying?
Yeah, you've got to have to do the finite element analysis. You have to have finite element information to put into it. Otherwise, it's
So the reason for my question, in my experience, we rarely, if ever, produce the kind of settlement that you see from an O'Reilly and U calculation.
yeah.
And in some circumstances, I feel we may be building in far greater factors of safety in terms of depth and
Yeah.
therefore cost
Mhm.
into some crossings.
Yeah.
And I was just wondering whether it's worth spending £5,000 up front to get a better answer from finite element analysis in order to get a cheaper solution than going with the standard kind of,
Yeah.
we know it'll be okay approach.
Yeah, well, it is conservative. Like I said, if doing your RLNU conservatively comes within the limits requested, then there's no need to take any further. Again, with the finite element, you do need more information.
Which isn't always possible.
Which isn't always possible. If it is an option just to drop it, take it a little bit deeper, it's often the cost effectiveness is going to be looked at by contracting.
Just another thought down from that, from the contracting side of it is you can have you build industry research, you can do the FE and everything, and you can have a more efficient but perhaps less robust design. But that means that when you then go under and hit a big boulder in the middle of the railway, you're very, very sensitive to that. So
Yeah,
absolutely.
Just something to flag as well. I'd say.
Who owns the risk?
Yeah.
Yes, it comes down to the risk and reward.
Yeah. So, like I say, you're going to have
I
more.
was going to ask you, could you put the percentages up?
The face wash.
Yeah. Well, there's 2 things. The soil does not fall into the tunneling machine. Yes? That I
Yeah.
will tell you right here and now. Yes? The ground squeezes into the tunneling machine because it has no option. Yes, when you remove soil in front of the tunneling machine, the ground above the soil squeezes the soil in towards the tunneling machine. Tunneling machines, by and large, have a face pressure either from slurry or earth pressure balance to counteract it. If any, and there are a lot of clients in this room, and most of them work on 1%. Although you can get those numbers up there, most clients won't let you go past 2%.
Mm-hmm.
So they are a little bit. I mean, by all means, you can adopt 8%, but I
They're
would suggest not.
conservative.
Most clients,
In some
the railway people will let you have 5 mil,
Yeah.
not 20 mil.
Mm-hmm.
Can I just ask a question in relation to this, which might apply to contractors? Is how can you adjust the way you operate your machine to control heave and settlement? Because I'm sure that comes into it as well.
Paying less driver.
That's one.
Yeah.
Pick the right type of machine. Pick the right type of the method you're going to use to excavate the soil. There are lots of different versions of soil conditioning and pressures you could use, and as mentioned behind me, driving styles. which can produce more or less settlement. A lot of the Crossrail machines that are 7 metres in diameter went through London, right through the centre of London, with less than 0.25% of face loss for a 7 metre machine.
Which is remarkable.
Yes? So, yes, in some types of non-cohesive soils where you're close to the surface, you get quite high settlements because they're instant. You physically struggle to stop them. By and large, most tunnelling techniques, most clients ask tunnelling contractors for 1% or less. And as I say, with the railway people, it's 5 mil. And that is normally somewhere in the half to a quarter%.
I would just add to that, Liddy. I've seen that before, and it's a bit nonsensical because you can't guarantee that you're making any percentage with it.
No.
You can say based on experience, this is what we can deliver, but it's dangerous.
I'm not disagreeing. The worst settlement I've seen in London was 3%. That was on the Jubilee line going through Green Park with an open face excavator shield that was 5.5 metres in diameter, and it was tearing the ground and they were going like Billy O. That's the worst I've seen in central London.
Was that in the London conveyor?
Yes, it was.
So adjusting the speed of tunnelling will affect your
Yeah.
Speed bad balance. How it's controlled.
Pick somebody, pick a reputable designer who assesses it conservatively to start with, but can take on board factors, and pick a reputable company who know how to select the correct type of machinery.
I mean, the caveat will be to, if your settlement is approaching the required limit, the caveat would be, this is the results based on an assumed face loss of 1, 2, 3%. So that's then passed on to the contractor that sort of provide that.
It's
guarantee
risk,
that.
it's risk management, isn't it?
It is, yeah. I mean, again, it would go back to being conservative. This is, it's
You would do
conservative.
damage risk assessments of any structure or service that you might be crossing. And if that showed that there's a risk of damage to that service, then you consider the cost of that damage and its repair, and you would appropriately move your tunnel or your crossing to suit that constraint.
Okay.
Another question.
Question?
I was going to ask a question earlier, sort of off the back of that really, how do you monitor settlement doing the actual works, and how often does the settlement profile, if not degree, match what you're modelling?
The settlement, there would be a settlement programme set up with alleys and a base station to the side of the railway or the highway, with sort of monitoring points fixed on a particular grid. Often when we sort of present these results, we'll advise the settlement programme, or the monitoring programme I should say, will give you a set of points based on the assumed settlement trough that we've calculated. We'll make sure the settlement extends to those limits. With rail, you can get little reflectors, you can put on the sleeper ends and things like that. Same thing on the highways, you can put, you can just actually laser target certain infrastructure, and it's monitored fairly regularly during the works. If we think it's going to be sensitive to settlement, the monitoring regime can be adjusted to make sure it's the continual monitoring through the progress of the drive. But yeah, generally, when we've come across something where the settlement encountered is way less than what we anticipated, it's something we just take on board, it's hard to present something to these authorities. They want to see some something like this in your analysis or spreadsheet to prove it, but when us just telling them from experience, it's not going to be anything like that. They want a bit more backup. We can advise that, we can mention that, and we can apply that to some degree to the choice of the volume of loss. Often the case, it's we can advise, but sometimes they want something in black and white. See what this provides.
It's often important to do pre-work monitoring for a period so that you can identify any seasonal movement. So there's an example of a rail crossing in Barking in East London, which was laid on basically timber on top of peat next to the river. And the movement of the overnight, as trains stop running, the track comes up and recovers from the movement of the trains during the day. But then there's a second profile overlay on that with the tidal effect in the peat. And on a crossing like that, it's very difficult to distinguish what you're causing from the underlying regime that's happening. I mean, that's an extreme example, but it's very personal.
Yeah, I've seen railway sort of jobs where there has been a marching regime on the railway prior to us, doing that UTX, and being on next to the railway where the train's gone past 100 miles an hour, the sleeper's moving it more than 5 mil.
Even a hot day will expand the steel.
The only area I might add to that is have all of these calculations and everything in place before any work actually starts, make sure I have a mitigation or like a response plan in place, and that's something that rather than upgrades. But for all crossing stuff, have it in place, because otherwise you can't normally turn around and do a stop. So I think you've got to get near any line of the limit, which is quite often not the ideal thing to be doing.
Yeah, it's with the monitoring programme. There'll be obviously the red, amber, green values, safe operating values are cell and green, and amber, maybe pause the works, discuss it, decide proceed, or off when you hit red and it's stopping. But sometimes stopping is the worst thing you can do. Carry on. So yeah, with the monitoring programme there's sort of what's the word? There's a process to follow if the limits start getting approached.
Okay, I think we should move on to the next session. And it's Graham Monteith again.
For the first time.
Selection and design of support and conveyance systems. It is the first time, not just before. You can stand this side of the table. It does make sure you can get it right on. It certainly makes a difference to that.
Okay.
That's the point.
Hi, I'm Graham Monteith. I'm the Bar Hales Engineering Manager for the Tunnelling Department. So my role in Bar Hale is basically managing underground risk through looking at solutions from tender through to delivery on site. And I'm just going to talk to you today, or for this first session, about the selection and design of support and conveyance fluids. So let's deal with the slurry, or the conveyance fluid first. This is a spoil removal system, basically. So its primary function is transporting cuttings from the cutter head through the slurry system and back to surface. It has a minor, sorry, that's not true. In some circumstances, it has a major impact on face support. But in cohesive soils, it has a minor impact on face support in terms of its formulation. But the pressure that it applies to the cutter head is important for face support. It also cleans the cutter head, so in clay soils which have a tendency to stick, then the slurry is there to keep the cutter head clean and to keep it working at its optimum. In some situations you might want to be cooling the cutter head. That really only applies in rock, where you've got high strength rock turning cutting discs, and it also provides some lubrication to the cutter head. We can't talk about the fluid without looking at the actual slurry system. So this is just a schematic. You've got a form of excavation at the front here, so because we're talking about slurry, we're talking about slurry shield microtunneling.
You've got a slurry pipe system, so you've got an inline and an outline. This is a bypass valve which enables you to switch flows, so you can turn flow from from the charge line to the discharge line if you need to. We've got some kind of separation equipment, and we've got pumps which will charge the slurry to the machine, and a pump in the tunnel which will, or in the shaft, which will discharge slurry back to surface to the separation plant. So this is just another shot of the famous photograph. It's picking up there a lot today.
I'm going to start asking for a commission on this one.
So just a few things again to point out. So we've got the main jacking rams. This is the charge line. We know it's the charge line because there's the flow meter on here. This is the discharge line. You usually have a pump at the bottom of the shaft in order to force the slurry up the shaft to the separation plant. And so you've got inline, outline, and there will be pumps within the drive. Obviously you get pipe losses when you pump fluids, so longer drives will have multiple pumps. That is very much dependent on drive length as well. So a small diameter, say a 600 shield, it's very difficult to get a pump that fits in a 600 pipe, and that's one of the limiting factors on how far you can actually drive a small diameter microtunnel. It's not always jacking load, it can be the ability to actually get your slurry back. So separation plants come in all sorts of guises. This is one of our modular systems based on a 20-foot container. So it sits on a tank which then has certain processes above it and then other processes above that. The primary function of the separation plant is to maintain the quality of the slurry that you're using by removing all of the cuttings from the return line. And we achieve that through various different processes. Most slurry plants have the same processes within them, they might be configured slightly differently. So just looking at the processes, this particular plant has a rotating chain conveyor, which is the primary screen, so that takes off all the big stuff that might come out of the machine, cobbles, boulders, down to about 6 millimeters. You may have a coarse shaking screen on some plants rather than this. So that reduces the load. So dependent on the ground that you're in, different grounds break down in different ways. So granular soil will not break down very much, so sands, gravels won't break down much, other than they may be crushed within the machine if there's a maximum passing size at the back of the screen. But then when you get into cohesive soils and silts, you could in some circumstances have 100% of the excavated material, white chalk, in suspension in very, very small particles, and that's very difficult to deal with. Another process that would be on most separation plants is a desanding or desilting hydrocyclone, and these work basically by introducing slurry at pressure at a tangent to the cone, which imparts spin onto the slurry, and the solids actually drop out of the bottom of the cone, they're forced to the middle and drop out of the bottom of the cone, and then the slurry is recycled through the top of the cone and goes on through the process to the next process. Dependent on the size of these, they will cut down from sand particles to almost silt particles, so you can get some silt out with this hydrocyclone. The last process, or one of the last processes, is using centrifuge. In fact, I missed a process. Yes. So all of these processes will discharge onto a fine screw. And what usually happens is that you get a filter bed on the screen. So sand, if there's sand particles within the slurry, the filter bed builds up, and that further filters what goes on top. So all of your silt particles and your smaller particles will go onto that. Centrifuge. So all of the other processes I mentioned earlier are in line, so that the whole flow goes through the course screen and the whole flow goes through the cones. But when you get to the centrifuge system, this is an offline system, so it is constantly running in the background, taking out small sub 3 micron kind of particles and below. And it works in a similar way to the cones, but it's actually a mechanical centripetal force which spins the slurry and forces the smaller particles to the centre, and then there's a scroll in the middle of the bowl which cuts the material out of the centrifuge. In certain grounds, you can't actually put enough force into the centripetal action in order to get the smallest particles out. And in that situation, we need to use an additive called a flocculant. So these are commonly used in water treatment, in sewage treatment plants, but in this process, what they do is they are a long chain polymer. They are either positively or negatively charged, dependent on the charge on the particles in the ground that you're trying to attract. So if you use a negatively charged flocculant, which is generally what does work, what they do is they grab all the positive charges on the little small particles, they clump it together, make it much bigger, such that the centripetal force can act on that larger particle and you can actually separate it out. Occasionally you need to use a positively charged flocculant or possibly both. So sometimes you might charge with a negative flocculant and then introduce a positive flocculant to grab those together. So you've got a combination effect, or you might just use a positive charged flocculant. Positively charged flocculants are incredibly damaging to the aquatic environment, so we try not to use them. They'll kill fish, and they're quite persistent. So they need to be managed very, very carefully if you are going to use them. And you need to have a way of stripping out that flocculant before it gets back into the slurry. You also don't want to overdose, because if you overdose, you start getting settlement in the tank and in the lines potentially. And then after all of these processes, the spoil is recombined. So what you don't really want is all the gravel in one, unless you want to reuse it, of course. But for disposal, you would put the gravel with the clay, with the silt, such that you get a homogeneous material that's much easier to dispose of off-site. It's often got very high water content, which could mean you need to leave it to stand for a while before you can dispose of it. It's quite difficult to handle. So in terms of the design of a slurry, if you consider that the separation plant is there to take solids out of the slurry, it's fair to say that in most circumstances, other than in granular soils or difficult situations, you would be wanting to just use water. A, it's cheap, and B, it has a very good cleaning capacity. There are additives and things that you might put in, but you wouldn't necessarily want to have a high solids mud like you would in a directional drill, because this slurry is not performing the same function. It's purely transportation rather than supporting an annulus. And if you consider putting bentonite into slurry and you're using a flocculant and you're in silty ground, you wouldn't want that, because you're just stripping the bentonite. It's great for the people who are selling you bentonite, but it's not that good for you as a contractor. Where you have either very challenging ground conditions, such as an open ballast, which needs the slurry to perform a part of its functions to support the ground, then you might look at using a bentonite or something similar. There are quite a few polymer formulations which are highly shear thinning, so when they have energy in them, they are almost like water, but when they stop, or you turn the pumps off, they gel. That has two important functions. If the slurry is escaping from the front of the machine into the ground, when the energy of the pumps dissipates, it gels and it fills the voids, and it provides both water cut-off flow and support to the ground. It also, when it gels in the pipes, it supports whatever your cuttings are in suspension rather than them all falling out the bottom of the pipe. And then when you start the pumps up, you've got to run them for half an hour to clear what's been settled in the bottom of the pipe. So it's an efficiency thing, it's a cost thing. So moving on to annular lubricants, the clues in the word. Pipe jacking is about jacking pipes through the ground, and one of the major limiting factors on A, how fast you can go, and B, how far you can go, is the friction that's generated between the pipe and the ground around it, or the material around it. So the primary function of an annular lubricant is friction cut. It also has the function of supporting the overcut annulus. So fluids are, in theory, incompressible. So if you fill that void with fluid and it can't go anywhere, in theory you are supporting the overcut annulus, which impacts on settlement. In some grounds, like in open material, there's very little you can do to actually fill the annulus. In a gravel, if we're honest, the gravel drops straight onto the machine as you cut it. You can't really support it. You can inject behind the overcut, and you will get some void filling, but in general, the lubricant there is purely for lubrication. It's not supporting annulus, not in a gravel. It will do if there's clay content that's locking the gravel together, but an open ballast. It's like a bucket of marbles. They'll just fall onto the pipe. So formation blocking in a lubricant is very useful in a fractured rock, for instance, where you might inject at pressure and the lubricant just disappears in fractures rather than actually staying in the annulus. So you might want to look at a formation blocking additive, which could be fibre or other proprietary things that are available. And also the control of swelling clays. So as an example, London clay and most clays have a percentage of their content made up of materials like bentonite and other materials called smectite, which is common in London clay. And there are capping polymers that you can insert into your lubrication, which will cut off water getting to the clay, which reduces its swelling capacity. And one of the problems in over-consolidated clays, like London clay, is you get a combination of friction issues. You get the over-consolidation, which is the pipe. As soon as you relieve pressure on the cut, the clay just wants to fall into the pipe because of its over-consolidated state, and then you get the swelling on top. So if you don't control that, then you limit your capability in terms of drive length. I think I've just been through most of that. These are the things to consider when you're thinking about your lubrication. Depth of drive is important because of overburden pressure. Whether you need interjacks or not, so using a very efficient lubricant might reduce your need for interjacks. I mean, on long drives, it's a very brave man that doesn't put an interjack in. But if you don't need it, all the better. One of the issues with interjacks is efficiency. Every time you energise an interjack, you're reducing the efficiency of your process. It takes longer, so you're crawling along rather than just entering the ground. Where you put your injection points is it a man access tunnel or not? So a 600 microtunnel is, by dint of the fact it's small, you can't put men up there. And you would only be able to inject lubricant directly behind the machine and directly into the entry eye. So it's very important on small diameters where you can't have intermediate injection points that you keep the annulus full at all times. You have a continuous injection regime. And you need to know what you put where so that you can understand if you're losing lubricant into the ground or not. So just to illustrate, I've got a couple of different examples. These are quite old jobs because they're from an old presentation. But so this is a project in London on the Nunhead to Deptford Millennium Main, which was supplying a water main to the what's it called? The big tent. The Dome, the Millennium Dome, that's right. So it's a 270 metre long drive, it's a 1200 ID slurry microtunnel. So the interesting thing here is it's an incredibly changeable geology. So we're in Woolwich and Reading beds which comprise consolidated clays, soft clays, sand, ballast, and they're all mixed. We've also got an interesting ground profile where the drive starts at roughly 10 metres deep, goes under a road which is in cutting, then goes under a hill, and then it goes under a railway cutting, and then it's finally recovered at about 30 metres deep. So we've got different overburden loads in very different ground, and the way that the lubricant and the slurry operated was very important. So in terms of the slurry, because we were working in clay soils and granular soils, we had to compromise on performance, and we chose to use a polymer-based shear thinning mud, because that will deal with both silt and allow you to deal with silt more efficiently in the separation plant, but it will also carry gravels. And that was used throughout. And then the lubricant had to be multi-purpose also. So that was I can't remember the exact formula, we took some advice on that, but it was a combination of virtually everything everything I mentioned to deal with all of those different conditions. So if we look at these are the jacking loads associated with this drive, and it's remarkable that the actual jacking load picture looks very similar to the ground profile picture in terms of loads. So as we advance under the hill, the jacking loads on the main jacks are increasing, and then we come to the cutting and they go down, and then we start getting loads again. And there's an overlay between friction loads related to length and the overburden pressure. This drive was completed one day before Christmas by the skin of our teeth, and we had to use all three interjacks on a 270 metre drive, which is, yeah. But then in contrast, so this is a very similar drive length, exactly the same diameter in Blakeney, which is on the Norfolk coast. We've got very little cover, so we've got opposite problems here. We're dealing with low cover and therefore low confinement pressure for the slurry. It's in weathered chalk, which is very weak, which is going to cause problems with the whole of the excavating material going into suspension. Groundwater surface, and it's an environmentally sensitive area. We were tunneling under a triple SI. So, in contrast, on this particular drive, the lubrication was less of an issue because we've got a pretty homogeneous material. Chalk's great for tunneling through apart from the separation problems. So we would have used a standard lubricant for the lubrication. There's nothing very clever about that. But the chalk itself is a problem in terms of the slurry and how it's handled. So chalk's very fine. It goes to sub-micron particles very quickly in the slurry line, and the longer it stays in the lines, the more of it breaks down. I think when we started the drive, we were probably getting 20% off the coarser screens. Towards the end of the drive, everything was coming off the centrifuge. And that chalk required treatment with a positive and a negative flocking in order to get it out of suspension. But on the same drive length, we never came off the main jacks, so we had less than 200 tons for the whole drive. And I think that's me done. I'm probably a bit quick. But if you've got any questions, I'm happy to answer some.
Okay, before we break for lunch, if there are no questions, we've finished a bit early, so we've organised the lunch to be ready by 12:30, so it should be out there. So we could start the next session at 1:30 rather than 1:45, which gives us a bit more time in the afternoon. I'd also like to say that during this lunchtime, you do have access to the Motorcycle Museum if you want to go in and have a look around. It's quite interesting. And one final thing about conveyance fluids. I've been involved in HDD work in the past, and there you have an expert on site mixing the mud, and it's quite an expert role. And we do have a couple of people from SIBO at the back who supply drilling fluids, and if you want to ask them any questions about chemistry or how they mix it or what mixes are available, you might want to talk to them.
I guess I should have said that the machine is really important, but the separation plant is as important. And personnel-wise, you're quite right. On a tunnelling scheme, we would have a mud engineer on the plant, and his job is to maintain the slurry in the right consistency, which is very similar to drilling.
Yeah.
In fact, most of them come from a drilling background.
Okay, perhaps we could just show our appreciation to the speakers. And we'll see you back here at 1:30 for the afternoon sessions when Tom Sangster will be taking over the session.